Good morning, class 10th. Today we are going to talk about common tangents. When the word common comes, that means there have to be two things. Here we are talking of a tangent which is common to two circles, and there are two possibilities in that case. As I have drawn the figures on the board, you can see in the first case two circles are here with the center O1 and O2. This is center O2. O1 and O2 are the centers of the circle. Capital R is the radius of this circle, and a small r is the radius of this circle. Two tangents are drawn. One is AB, line AB, a straight line which is touching the two circles at point A and B. There is another line which is touching the circles at point C and D. What is to be noticed is that both the circles are on the same side of the straight line. It is below AB or it is above CD. That means both circles are on the same side of the line. Whatever the tangent is there, this AB and CD are called common tangent. They are called common tangent, and these are called direct common tangent. These are called direct common tangent because both the circles are lying on one side of the tangent. They are lying on one side of the tangent. Like in this case I showed you, they are lying below AB or they are lying above CD. So these kind of tangents are called direct common tangent. Both circles are on the same side of the tangent. These are called direct common tangent. And if we have to calculate the length of the direct common tangent, I have written AB and CD both will be equal. These both tangent, length of both the tangents will be equal. AB will be equal to CD will be under root O1 O2 whole square. That means the distance between O1 and O2 will be calculated. You will take the distance between the centers of the circle O1 and O2 and square it minus the difference of the radius. This is R. This is a small r. Take the difference of the two radii, r minus r whole square, and take the under root. You will get the length of the direct common tangent. You will get the length of the direct common tangent. Now let us talk of the another possibility. This was the possibility of common tangent. There is another possibility. Like here, in this case, if you look at this figure here, then you will find that there are two tangents which can be drawn to these two circles also. The only thing is that both the circles are lying on the either side of the tangent. They are not lying on the same side as in this case. Like if you see, I have drawn a line like this and it touches the circle, bigger circle at P and the smaller circle at Q. So the P, it is lying below P, the bigger circle is lying below P, but the smaller circle is lying above Q. That means they are lying on the either side of the tangent. Look at the another line. I have drawn another line, another straight line, which is touching the bigger circle at R and the smaller circle at S. But again the question is that the bigger circle is lying above R and the smaller circle is lying below S. That means the bigger circle is lying above line RS and the smaller circle is lying below line RS. So in this case, the two circles are lying on the either side of the common tangent. These kind of common tangents are called transverse common tangent. They are called transverse common tangent. These are called transverse common tangent. In transverse common tangent, both the circles are on the either side of the tangent. In direct common tangent, they are on the same side of the tangent. Like either they are below AB or they are above CD. Here, if one is above, then the other circle is below the line. Similarly here, it is below, then it is above. Like we calculated the length of the direct common tangent, we can calculate the length of the transverse common tangent also. The length of PQ will be equal to RS. Length of PQ and RS will be equal, and it is given by the formula under root, find the difference, the distance between the two centers, O1, O2 whole square, minus R is the radius of the bigger circle, small r is the radius of the smaller circle, so r plus r whole square. In that case it was r minus r, here it is r plus r. So we can calculate the length of the direct common tangent and length of the transverse common tangent. This is the only thing which you have to learn in this. There is no construction given to you for direct common tangent and transverse common tangent, though it is very simple, and in case it will be required we will deal with it also. We have the theorem where it says, the statement is, if two circles touch each other externally or internally, like you see here the first figure, two circles with the center A and B are touching each other externally at point P. Here the two circles with the center A and B are touching internally. It says if two circles touch, then the point of contact lies on the straight line joining their centers. What does it mean? This is the point of contact where they are touching. That is, there will be only one point of contact whether they are touching internally or whether they are touching externally. We have both the figures here. In the first figure, the two circles with the centers A and B are touching each other externally at point P, and here the two circles are drawn so that they touch each other at point P, but they are the smaller circle is inside the bigger circle. In first case they are touching externally, in second case they are touching internally. A and B are their center. What is required to prove is that we have to prove that point P lies on the line joining A and B. If we join the centers of the two circles, then the point of contact will lie on that straight line. That means P will lie on AB, whether externally or internally touching. The point of contact will always lie on the line which is joining the centers of the two circles. That is required. Now, what have we done in the construction? That we have drawn a common tangent. We have drawn a common tangent at point P. We have drawn a common tangent. That means you're drawing a tangent at point P and tangent at point P here also. That means a straight line touching both the circles at point P in first case as well as in second case. Now let us see what are we saying. In the first case, just look at the first figure. Angle APT will be how much? 90 degree. Why? This is the property of a tangent. What is the property of a tangent? The tangent and radius are always perpendicular to each other at point of contact. That is the first thing which we had learned in the circle, that the radius and the tangent are perpendicular to each other at point of contact. So I am saying angle APT is 90 degree, what I have written here. Angle APT is 90 degree. Then I have written angle BPT is 90 degree. Why? The same logic. The radius and tangent are perpendicular to each other. And if I add this APT plus BPT, if I add up APT plus BPT, what will I get? 90 plus 90, which is equal to 180 degree. That means this angle APT becomes how much? 180 degree. If it becomes 180 degree, that means what? That means APB is a straight line. So P will lie on the straight line joining A and B. That is what we have said. APT is 90 degree, tangent is perpendicular to radius. BPT is 90 degree, tangent is perpendicular to radius. For the first figure we are saying APT plus BPT will be equal to 180 degree. That means the whole line, the angle APB will be 180 degree. And if it is 180 degree, that means APB is a straight line. That means P lies on the line joining A and B. This is the first case. Now let us see the second case. In the second case, what we are saying is again that APT will be 90 degree. The same reason we are applying, that a radius, AP is the radius of the bigger circle and PT is tangent to that circle at point P. So the angle APT will be how much? 90 degree. It will be 90 degree because radius and tangent are always perpendicular to each other. Radius and tangent are always perpendicular to each other. So angle APT will be 90 degree. Now for the smaller circle, B is the radius. B is the center. BP is the radius. So BP and PT will be also perpendicular to each other because the radius and tangent are perpendicular to each other. That means APT is 90 degree is equal to BPT. And P is the same point. At P we are getting two angles 90 degree, whether BPT or whether APT. AP and BP both are perpendicular to the same point. Only one perpendicular can be drawn on a line through one point. That means P lies on the line joining AB. P lies on the line joining AB, and that is what we had to prove. In both the cases we have shown you that whether the circles are touching externally, P lies on the line joining AB by saying the angle APT and angle BPT are 90, so when they are added they become 180 degree and they will make a straight line. Here in case we are saying APT and BPT both are same and they are making the same angle at the same point. That means P lies on the line joining AB. So the point of contact of two circles touching each other will always lie on the line, on the straight line joining the centers of the two circles. Actually, next theorem we are going to deal with segments of a chord. So before I do the segments of the chord, what I want to do is I want to make you understand or make you aware what are segments of a chord. We have two figures here drawn on the right side of the board where AB is a chord, AB is a chord in the circle, and P is a point on the chord but inside the circle internally. Point P is in between A and B somewhere. It could be anywhere. So PA and PB are called the segments of the chord. PA and PB and PB are segments of the chord. Are segments of the chord. Segments of the chord AB. Of the chord AB. This is in this case where P is a point which is in between A and B. But there is another possibility if you look into the second figure that AB has been extended to a point P and point P is dividing the chord AB externally. It is dividing the chord externally. Then also PA and PB are the chords, are the segments of the chord, are the segments of the chord AB. This is important to understand because we will be dealing theorems. One will be when the chords will be intersecting internally, and one will be when the chords will be intersecting externally. So in both cases you must understand what is the segment of the chord. Here PA and PB are the chord segment of the chord. Here also PA and PB are the segment of the chord. Okay. This is the second part. First part we discussed when we said if two chords of a circle intersect internally, that theorem I've already done. Now we are talking or externally. These are two chords AB and CD. They are extended and they cut each other or intersect each other at point P. So we get two segments of the chord. Like for this chord AB, I get PB and PA, and for CD I get PC and PD. So it says if two chords of a circle intersect internally or externally, like in this case, internally we have already finished. Externally now we are talking, then the product of the length of the segments of chord are equal. So what will be the product of length of segment? PA into PB will be equal to PC into PD. That is what we have to prove. Given as chord AB and CD are intersecting externally here at P as shown. Externally at point P as shown, we have to prove that AP into PB is equal to CP into PD. Now what we have done is join A to C construction, join B to D. That is the construction part. We have joined A to C and B to D. And we will prove the triangle ACP and triangle BDP to be similar. For proving any two triangles to be similar, what we need to do is we need to prove them to be equiangular. So we will try and prove the two triangles to be equiangular. That means we are going to prove each angle of one triangle is equal to each angle of the other triangle. For example, if you see here, I am saying angle CAP is equal to angle BDP, X and X as shown in the figure. Why are they equal? Because if you look at the figure, ABDC, it is a cyclic quadrilateral, or ACDB is a cyclic quadrilateral. What is a cyclic quadrilateral? A quadrilateral whose vertices are lying on the circumference of the circle. So A, C, D and B are lying on the circumference of the circle. So it is a cyclic quadrilateral. It will follow the property of cyclic quadrilateral. And what is the property of the cyclic quadrilateral? First theorem we had discussed, the opposite angles of cyclic quadrilateral are supplementary. And second was that exterior angle of a cyclic quadrilateral is equal to the interior opposite angles of the cyclic quadrilateral. So here I have said angle CAP is equal to angle BDP, because BDP is the exterior angle of the cyclic quadrilateral, because we have extended one side of the cyclic quadrilateral. ACDB is cyclic quadrilateral, and I have extended the side DCD to point P. So the angle BDP is exterior angle of the cyclic quadrilateral, and that exterior angle is equal to angle A, interior opposite angles of the cyclic quadrilateral. So we have said CAP is equal to BDP X, like we have shown in the figure. Next is angle ACP is equal to DBP is equal to YC with the same logic. Because I have the cyclic quadrilateral ACDB if you look into the figure, and if I extend the side AB to a point P, then angle DBP is the exterior angle. Angle DBP is the exterior angle which will be equal to the interior opposite angle, that is angle C. So these two angles have become equal, and third angle of course is common angle. Angle APC is equal to angle BPD. This is a common angle. We need to prove only two angles, but we prove generally all the three angles. When two angles are equal, then the third angle of the triangle will automatically become equal by the property that the sum of the interior angles of a triangle is always equal to 180 degrees. Now once we have proved these two triangles to be similar, then what are we saying? That CP upon BP will be equal to AP upon DP will be equal to AC upon BD. That is, the ratio of the corresponding sides will be in proportion. And for finding out the ratio or for finding out the corresponding sides, what we do is we just remove the middle alphabet from the angle and we get the corresponding side. Now I need CP, AP, BP, DP, and I don't need AC, BD, so I just ignore it and cross multiply these two ratios, and I get AP into BP is equal to PD into PC. So if the two chords are, whether they are intersecting internally or whether they are intersecting externally, in this case, the product of the length of segment of the chords will be always equal. Thank you.